once again, I've got a D flip-flop used to make this T flip-flop, and the D flip-flop has just a special feature to kind of jump start it, right? And it's got this tri-state buffer, meaning that when this initialize is set to a 0, it's like the end of this isn't connected at all. It's completely disconnected. It's not driving a 0 or a 1. It's just nothing. It's floating. And so that allows this pull down resistor to force it to be a 0 until it's initialized. And then this OR gate with the inverted inputs is now driving this output, not the resistor. And that comes through all the way to the flip-flop. And here is our T flip-flop. So when I want to enable our T flip-flop, I just click enable, and now I can write it. So, and once again, that's just to deal with the way the simulation environment works. So the toggle flip-flop is actually very, very straightforward. We can make it out of a JK flip-flop as well, but here I just chose to use a D flip-flop. And here's what happens. One interesting thing is that our right input is the clock signal, right? T, our toggle signal, just goes to the clock. And our Q naught is writing to D, which kind of makes sense, right? If D is what we want the next output to be, it should always be the opposite of what the current output is, which is Q naught. And so as I toggle this, right, you can see it's rising edge triggered. As I toggle this, it's just going to toggle the output as well, right? So as the clock just kind of 1 0 1 0 1 0, it's just going to keep flipping Q. So these devices are actually very useful for bigger devices called counters, because counters are just toggling bits in a certain fashion that allows us to count upwards or downwards in binary.